We're back for one more lecture about mineral processing, and today we're going to be talking about mass balancing. And if possible, keep with you some paper and pencil because you're going to need it. Okay? So before we start discuss about mass balancing, let us understand a little bit why should we be considering this? Okay, why mass balancing is so important. And normally, if you are in an internship in a company, they're gonna send you straight to mass balancing, and that's actually a very good practice because if you get in touch with the company mass balancing, then you're gonna know a lot about that company. Okay. So if you want to take a look and assessing, troubleshooting, or even improving a plant performance, go for mass balancing. Okay. If you want to control or monitor your plant operation, definitely you need mass balancing. Even if you want to take a report or an accounting regarding the metal production, mass balancing is the way to do it. Okay. But nevertheless, if you're into stock movements, mass balancing can also help you. So you can profit a lot if you have your company mass balancing up to date. Okay. And that's what I'm going to try to show you. But before anything else, one word is quite important for us today, and it is about reconciliation. Okay. So what is reconciliation when you talk about mineral processing and even thinking a little bit bigger mines in general? When we go to the geology and we go to the mine planning, we have an idea of what kind of ore we'll be working with, what kind of material we're going to be feeding in our mineral processing plant. But actually, when we do it, we don't know exactly the grades and the amount of ore that we're actually delivering to the mineral processing plant. We have, again, an estimation. We're going to know for sure after we have all the material passing through our company, okay? And that's why we're going to have data and reliable data to sit down and come with these figures. Or we produced this amount of this tonnage of material, okay? Because we're going to sell it. And then we're going to have profit, okay? And what is reconciliation? It is like going to a meeting, we're going to sit down and we're going to discuss. Oh, you promised me this amount of material, but on the other hand, you deliver me just this. You promised me this grade of ore, and on the other hand, you deliver me this grade, okay? So reconciliation is pretty much trying to put people from the extraction with people from the production and make them come with some sort of agreement, okay? What kind of ore was actually delivered and what kind of ore we're expecting to be delivered. And this could sound like easy to do, but definitely that's not the case, okay? Because if we take a look at the mineral processing plant, of course, mass goes in and mass goes out, okay? So if we think just about this, would be a very, very simple equation, okay? Because we have the pulp feed rate, and normally we're talking about tons per hour, but could be tons per day, month, or even year. And then we have like the tailings, would be the material that we reject in our mineral processing plant. We don't accept this material, so we reject it. And then we have our cleaner material, our material that we're gonna or send to another route in the future, or we're gonna sell it, okay? So would be something like this. Mass go in and two masses coming out, okay? And that's actually feasible. You can do your mass balancing by this black box, okay? I just put a big black box around my mineral processing plant and say, okay, everything that goes in has to come out, okay? And again, it works. But then again, I'm not producing only tons per hour. I have to consider the material that actually I want to sell. So for example, if I'm in an iron ore mine, I have to consider the grades. How much hematite do I have in my feeding? How much hematite I'm losing to the tailings? Because don't get me wrong, you always gonna lose some of your material in your tailings, as much as you're gonna have always a little bit of tailings in your concentrate, okay? And in the end, how much hematite do I have in my concentrate? So I have to couple the grades with the tonnage. And if I want to extend this, I have to couple with particle size distribution and particle tracking and so on. So we can even add more information in our mass balance, and then in the end we're going to have a big data. Literally, we're going to work with big data and data science. So let's start simple, keep this small, and today we're going to focus only on the tonnage and on the grades, okay? But if that's the case, we could enhance our comprehension and go further, okay? So this is a regular tank cell for flotation, and that's one of the possible representation for tank cells. And as I mentioned before, we have the grade and we have the tonnage that I'm feeding my tank cell. And on the other hand, I have the concentrate and the tailings coming out of the tank cell. Okay, so I could use these letters to define the features, and I'm going to use capital F as the feed in tonnage per hour or per day or per month, tonnage per a time period. And I have the lower f as the grade, okay? So by the same analogy, I'm going to the concentrate being capital C as tonnage, and the grade, the small lowercase for C for the grade. And the tailings, I'm gonna use the letter T, okay? And the first equation that we can draw about this is the feed is going to be equal to the concentrate plus the tailings. And by using this equation number one, I'm going to talk only about solids. Okay, if I want to introduce water, and I can do this, and I should be doing this, I'm going to have also a water balance. So not only mass balancing, but also water balance. And for those, the first examples that I'm going to show today, I'm going to focus only on the dry part of the mass balance. So everything in here is going to be about the solids. Okay. Nevertheless, we could use the same equations, just changing grade for water or things like that. So the second equation is going to be what? I'm going to multiply the grade versus the tonnage versus the flow. Okay, and by doing this, for example, the hematite grade versus the feed flow, I'm going to have what? The hematite flow. So the second equation could be written like this. The amount of hematite that I'm going to feed my tank cell is going to be the same amount of hematite that is going to the concentrate plus the hematite that I'm losing to the tailings. It makes a lot of sense, okay? Because again, mass in, mass out. And the numbers has to close, right? So if I don't have any kind of other mass being loose in our equipment or in our processing plant, or if I'm not producing mass, it would be quite awkward to produce mass, then the equation is going to be correct. So number one and number two are the most used two ones, and I'm not going to say the most important, but everything starts with this two. So it's quite important for you to understand that mass in, mass out. Always remember this, okay? And can save you a lot of trouble. But actually, when we're going to solve the problems, it's not good for us because it's not so easy just to keep these letters. So it's good for us, it's a very good practice if you draw a flow sheet and you add these informations on your flow sheet in small tables. So for example, for the feed, what we're gonna have is the solid flow, then we have the water flow, then we have the grade, the solid content, and the density of the pool. So again, you could add a lot of extra information in your feed box, okay? But that's the least amount of material that you want to have in order to perform a good mass balance. So if you go to Excel, for example, Microsoft Excel, you just input those small tables or small boxes for every kind of flow that you have, and you're going to start to make this characterization of your flow, and in the end you can close your mass balance. It's going to take you some time, but in the end it's going to be quite nice. Okay, so this is actually a real example. This is coming from a place called Paragominas in Brazil, and they are located 60 kilometers away from the city Paragominas. Okay, and that's why the mine have this name, coming after the city. And it is an open pit mine, and they belong to a company called Alunorte, and they stay on the area of a big city called Barcarena, and they produce aluminum. Okay, so as you can see over here, that's their mass balance. So we have this M1 and M2 being mass 1 and mass 2. Mass 1 is a run of mine, mass 2 is material coming from the stockpile. Then I'm going to feed the crushing, and then I have M3 because it's going to be just one mass coming out of the crusher. And then I'm going to the stockyard, and as you can see over there, I have M4 and M5. Probably we have two different heaps or stockpiles in this stockyard. One for number 4 and another one for number 5. This is quite regular operation. If I'm reclaiming the mass M4, I'm feeding the mass M5. Okay. Nevertheless, I'm going to have one mass coming out of the stockyard and into the mineral processing plant, and we call this M6. So I'm going to deliver this material to a silo, and this silo can feed actually two plants, plant 1 and plant 2. And that's why I have M7 and M11. Okay, why 11? Because M8 is going to be material coming out of the plant. Okay, being introduced in the plant as a delta M8, and then we have M9, M10, and so on. So as you can see over here, we have a lot of masses. Okay, and going to be all those masses interchanged in one process to another. That's why we have these arrows connecting the process and delivering masses from one process to the other. And this delta in being written in red, it's quite clever, because definitely you're not going to be able to feed 100 tons per hour in a mineral processing plant and draw 100 tons per hour out of it. Okay, you're always going to lose some material. If you're in a lab, you're going to lose material. And actually, in our lab's operation, that's going to vary a lot, but something around 1% up to 5%, it's quite normal. If you consider that you're going to take the material, you're going to grind it, and you're going to mill it, and then you're going to, for example, dry it, and you have homogenization, and then you're going to have the samples that you're going to use in flotation, 5% is quite okay. You're going to produce powder, and you're going to eventually lose material. Okay, so yeah, you have also a delta, and this delta is going to be negative. But nevertheless, let's keep with that in mind. Okay, we're going to have this flow sheet, and this flow sheet has to be as close as possible to the reality. And then we have more equations, and we have more terms to understand. The first one that I'm going to show you is recovery. Okay, so what is recovery, and why recovery is so important to us? Because recovery is going to correlate the amount of material, amount of elements that I want to produce in order to the amount of these elements that I have in my feeding. So it's going to give me an idea, literally, on how much material I could recover from my feed. Okay, so if I have this number close to 100%, then I have a good operation. Yeah, very good operation. But recovery, it's all connected with grades. Okay, in here we're not going to be talking only about mass. I can calculate this the same number using masses, but I can also calculate regarding grades. Okay, so let's take a look at the first equation. So we have this lowercase c, lowercase f, and lowercase t, and they're going to stand by concentrate, feed, and tailings. So I'm going to multiply our grade in the concentrate to the difference between the feed and the tailings, and I'm going to divide this by the feed multiplied by the difference between the concentrate and the tailings. Okay, and again, that's going to be a number between 0 if you're not lucky and 100% if you're really extremely lucky. Okay, but one thing that is important for us, how can I maximize my recovery? If I maximize the terms on the upper part, on the numerator. Okay, so to doing this, okay, I have to also minimize but the denominator. Okay, it's also a possibility. But let's take a look at this. If I want to increase my first part of the equation, I have to increase the concentrate. That's possible. So if I increase the C, okay, and decrease, for example, T or F, that's going to be good for me. But actually, when I try to do this, I always reduce my production. Okay, when I'm talking about tons. So tonnage is going to go down as much as the recovery goes up. So the rule of thumb in here is going to be something like this. If you want to produce a high grade material, you're going to produce a small mass of that material. Okay, and that's go for everything. And it actually is work. Okay, in the very, very few cases, you're going to see something like the grades going up and also the production going up. Okay, that's not normally, but eventually you can even have something like this, at least for a certain period of time. After that, what you're going to see is two curves, and if one goes up, the other goes down. Okay, and let's move a little bit for our first example. So now we can make some calculations. Okay, and this one is a very good example, and it's coming from 911metallurgist.com, and actually that could be something real. Okay, so we have a copper concentration plant, and we be milling 15,000 tons per day of copper ore, and I'm going to feed this chalcopyrite in order to have this concentrate coming out of the equipment. So what kind of equipment? Let's consider flotation for a while. Okay, so I'm going to deliver 15,000 tons per hour to a flotation plant, and what's going to come out of that, it's written in the sequence. Okay, so I'm going to be adding my chalcopyrite in a grade of 1.15%, and I'm going to be able to produce a copper concentrate with 32.7% of copper. Okay, so understand this, we're talking only about copper. If I gave to you the grade of chalcopyrite, then your mass balance would be chalcopyrite, it would be mineral mass balance. Okay, we can do this in one way or the other, that's not a problem at all. But depend on where you are, people prefers to refer their mass balance to a chemical species, to a mineral, or even to an element. So when we talk about iron ore, again, iron ore, we always talk about Fe2O3, hematite. Why? Because that's the figure that's going to be coming out of the X-ray fluorescence. So we just send our material for a chemical assay, and we're going to receive as iron oxide, and we're going to be referring everything about iron oxide. Okay, if you come to niobium here in Catalan, we're not going to be talking about iron anymore, we're going to be talking about niobium. But then again, the XRF is going to give me what? Oxide composition. So I'm going to receive my data, my assay return is going to be coming as a niobium pentoxide. Okay, so I would be referring all the time as niobium pentoxide. So what is your cutoff grade? 0.8% niobium pentoxide. Okay. If you go to phosphate rock, the same. Okay, but in the case of the phosphate rock, we're not going to be talking about apatite. We're only going to talk about phosphate oxide. So in this case, P2O5. So phosphate pentoxide. And again, many examples can be given just like this. Okay, we're going to use our characterization machine, our assay machine as our result. Sorry, someone is going to join us. As a directly result about our calculations and our inputs. So we're just going to use the same number, the same figure, and it's going to be easy to correlate one to another eventually. Okay. So in the end, we're going to lose something like 0.18% of copper in our tailings. That's quite good operation. If you consider that we have 1.15% and we have a tailings with just 0.18, it's even too good to be true. But nevertheless, let's see how can we calculate this. So guys, we have just one mass in our balance. We only have the feed, but nevertheless, it's possible to calculate the recovery, and that's why I want in this first example just to know the recovery of copper. Okay, I'm going to just go straight to the grades. Okay, so it's just a case of replace the numbers in our equation and just do the math, and it's easy to do this math, and in the end we're going to have a recovery around 85%. Okay, what kind of conclusions can we draw after this number? Okay, first conclusion is the majority of my copper that feeds my mineral processing plant, it's going to be delivered to the concentrate, and that's quite good. Okay, that's the way it should be doing. Okay, I'm not throwing my copper on my tailing dams. On the other hand, I put my copper, or the majority of my copper, in our concentrate, but I'm still losing material. And how much copper I'm losing? I'm losing something around 15% of my copper. Okay. And on the other hand, how much mass we're talking about? Okay. That's the next thing that we're going to see. Because in the end, what we're going to sell, we're going to sell mass. Okay. And we want to sell this mass. And we're going to receive money regarding how much mass we're delivering. Okay. Of course, grade is quite important, and one thing is going to be actually in our contract, and the grade that I'm delivering my concentrate. So have this in mind all the time. But on the other hand, let's consider this example. Okay, I was hired to deliver a copper concentrate having only 30% of copper on it. 30%. As I mentioned to you before, if I increase the grade, okay, I increase the recovery, automatically I will be decreasing the mass produced in my mineral processing plant. So if I produce a copper concentrate not with 30% but 32.7%, just like this example, probably I will be producing less material than I should be producing if I deliver a copper concentrate with only 30%. Okay? And one of my students one day came with me with the brilliant idea. He came to me and said, "Oh, professor, don't worry. If you produce 32.7% of copper concentrate, that would be okay because it's going to be the end of your process. You just take something of your tailings because there is 0.18% of copper in your tailing and just mix with your concentrate and deliver 30%. And he's actually right. Okay, and we do this. We just mix the concentrate with part of the tailings in order to reach the grade that I have to deliver to my clients. Okay, so if the case is to not enrich, but to make my concentrate a little bit more poor, it's going to be quite easy. I just take the tailings and mix a little bit of it with my concentrate. And in the end, everybody's going to be happy because my client, he would be receiving exactly the material that he paid for it. Okay. And I would be delivering more material than I should. And I'm going to be paid for this. Okay. So in the end, I'm going to be paid as a concentrate, but I'm going to be delivering part of my tailings. It's a very good situation for me. It's a good scenario. I like it. But nevertheless, okay, keep that in mind. Always, always, always keep that in mind. If you want to produce higher grades, you're going to be producing lower tonnage. Okay, so we have this relation. It's a direct relation. So another thing is, would be possible to evaluate the other two flows because I know how much material I'm feeding in my mineral processing plant. 15,000 tons per day. Okay, and how about the concentrate and the tailings? How can I split that mass? I can also use the same equation and the first one to evaluate this. Because if I rearrange the terms of the first equation, I know that the tailings is going to be what? The feed minus the concentrate. And that's the standard, okay? That's quite easy. But if I know how much is the feed, and I know in this case it's 15,000 tons per hour, tons per day, sorry, and I know that my concentrate is 400, almost 445, 447.42, I can evaluate this easily like this. So the thing is in here is how can I get to this number? How can I calculate my concentrate? And I can do this easily by using the same recovery equation because I know that the recovery is 84.81%. Okay, and I know that I can also evaluate the recovery using this equation. So if I combine this one with this number over here, I can come with the concentrate. Okay, so again, if I have the recovery and one of the flows, I can automatically calculate the other two. And it's easy to do this. Okay, but I have to calculate the recovery first. Okay, just go for the recovery. And one thing that we also can draw as a conclusion of this small experiment over here is what kind of chemicals assays should I be doing? And here in Brazil, I'm sad to say to you that people do things like this. They eventually collect some samples from the feed. Okay, they can do this like twice per day, 3 times per day, even a little bit more, but they're going to collect a few samples from the feed. Okay, but they're going to collect more samples from the concentrate. Definitely. Why? Because they want to know the quality of the product. So they're going to connect more samples from the concentrate. And they're going to analyze those samples. And they're going to evaluate the tailings that are going to be coming out of this. So it's not regular in industrial operations in Brazil that you sample the same amount of samples on the concentrate and on the tailings. And you should be doing this. You should be collecting samples from your tailings. Because mathematically speaking, you can use one of the flows to make your evaluation. You can evaluate how much material you're losing to the tailings by using, so to say, the feed and the concentrate. But then again, you don't know for sure if your calculations are accurate or not. Okay. So when you do this differently, when you collect samples from the three flows, the feed, the concentrate, and the tailings, and you try to apply those equations that I'm showing you right now, actually it's not going to work. Because if you evaluate the amount of mineral, interest mineral that you put in your flotation, it's not going to be directly the sum of the floated material and the sank material. Why? Because we always have some errors to deal with, okay? And then my mass balance is going to change from this first equation right here, quite simple, to an equation slightly different because I'm gonna have to input the feed error, the concentrate error, and also the tailings error. And how can I measure those errors? By performing a lot of assays. Okay, so in this case, what I want to do and what I need to do is have an idea of the standard deviation of my grade in these three flows. Okay, and that's a very beautiful Six Sigma project. Okay, so if you're into this quality control and quality production, definitely take a good look at lean production and Six Sigma, and then apply all of that statistic into this calculation. Please, Ramon, feel free to ask your questions.
Was the feed should be a dating or is it really feed?
No, in this case, we're talking about the real feed. Okay, so if you come back in here to that representation that we have over here, we're talking about the material that we feeding our equipment. So in this case, how much material I'm feeding the flotation, okay, or the grinding and so on. So yes, we're talking about the feed, and then we can evaluate, and that things that what people do in Brazil. We have this, okay. For example, we have one sample per hour, and in here we have one sample every 10 minutes, and then I just calculate this. I don't have the chemical composition of the tailings. I'm going just to calculate because I know the material that is feeding the flotation tank, and I know the material that is going out as a concentrate, and I just calculated the tailings. So all the errors is going to be inputted to the tailings, and that's not correct. I shouldn't be doing this, okay? But since I'm just throwing away the tailings, makes some sort of sense doing this. But then I have the reconciliation, and nothing is going to be closing in the reconciliation because I'm committing some errors and people knows about it, and instead of just trying to minimize and to work with my errors, I just said, doesn't care, I'm just gonna put everything to the tailings. So, yes.
Okay,
I'm not sure if
but in your the equation where you calculate where you put the feed is
there's a question over here.
where the feed is the balance feed is tailing plus concentrate. Next one.
Okay, there's one.
Yeah, does I mean here you are calculating the tailing, right?
Yes, that's right. And here I'm calculating just, sorry, now I understand. This is wrong. Okay, I get it now. So this would be T. You're correct. Okay.
Yeah,
Yeah,
yes.
I'm gonna make these notes and I'm going to correct this. So in this light material that I'm going to deliver to you, that's going to be a T over here. Thank you so much. Okay. We have a very good professor in Brazil, and he knows all about mass balance. I'm talking about Professor Chaves. And sometimes when you read his books, you can eventually find something like this, some mistakes like this. And when you talk to him, he said, "Oh, that's very nice. I just input those mistakes over there to take care and to see if you are paying attention to my lectures." And yes, you were paying attention. So congratulations. That wasn't the case. That was my mistake. Okay, but nevertheless, that's a very clever way out for a professor. Okay, so let's keep going then. So now let's talk about mass recovery. Now we can talk a little bit about production. Okay, so mass recovery is also called as mass yield, and I think both names are equally correct, and they also make sense because yield is going to be the amount of material that you're producing. It's a mass material, and the mass recovery is the same concept as recovery before, but now we're talking about mass. So in some countries, you're gonna see not only recovery, but the people are going to address recovery as metallurgical recovery. Okay, so if you come to a place and people talk to you about metallurgical recovery, it would be like recovery. And on the other hand, you can talk about mass recovery or mass yield of your process, and it's going to be the same. Okay, and some authors they're going to use RM for mass recovery or Y. Okay, so you just choose whatever you prefer. And if you go to study in the Wills and Finch book, that's going to be a Y over there because they're going to talk about mass yield. Okay. Nevertheless, they're both correct. And in here, I'm going to use the both names. I'm going to use in some examples mass recovery, in another examples mass yield, in order to train you guys to use both as the same. Okay, so in this case, what I'm gonna have is I'm just gonna remove the grades from these two flows. Okay, so sorry, and at the beginning I have this F and C over here, and I'm just going to remove those. Okay, so I can evaluate the mass yield as being a division between the concentrate and the feed, or I can do the same by using the grades also. Okay, so I can use both equations and the result should be the same. Okay, but as I mentioned to you, if I go to an industrial operation, the result is not going to be the same. Okay, why? Because I have some errors measuring the flows as much as I have some errors evaluating the grades. Okay, so if I couple these two equations, now I'm not talking about one equation, but it's two, then I could evaluate the errors between these two approaches, working with the flows and working with the grades. Okay, and that would be actually a good thing to do. But nevertheless, industrially speaking, people don't do this a lot. Okay, they should, but they don't do this. So how about the mass recovery for our first example? Can we continue the example and evaluate the mass recovery? Of course we can do this because we have the concentrate and we have the feed. I just need to divide one per the other, and then I have this. So guys, take a look at this. At the first number, we're quite happy because we could recover 85% of all copper that we had in hands. 85%. Okay, when we go to the second number, then we could become a little bit sad if we don't know how to read this. But what I'm seeing right now is only 3% of everything that I feed in my tank cell, in my flotation circuit, I'm going to take it back as a concentrate. Just 3%. Okay. And is this a good thing or not? Yeah, that's a bad thing because I'm going to have 97% of everything that I feed in my mineral processing plant, specifically my flotation plant, as tailings. So I dig up 15,000 tons per hour, and I'm going to have to pile this up or to stock this somewhere else, and I'm just going to profit only with 3%. But it is what it is, because if you're working with a low grade feed, that's what you're going to see. Okay, you're gonna lose a lot of, no, you're not losing anything, but you're gonna be working with a lot of tailings. You have to have this in mind. Okay, so if we talk about niobium, 0.8%, almost everything is going to be tailings. If you consider now gold, in gold we're talking about 1, even sometimes 0.5 ppm, 0.5 parts per million parts, and this made of gold. Okay, so yeah, I have almost everything made of tailings. Okay, I don't have almost nothing regarding gold, and I have to keep all the tailings safe. And here in Brazil, we are responsible for our tailings for the next 100 years after we produce them. Okay, after producing the tailings, I have to take care of it for 100 years, and yeah, this is a lot of time. But nevertheless, it's going to be a lot of mess. That's why you have to have this figure calculated and estimated, and you need this number in order to allow you to perform a lot of calculations and, most important, to plan correctly your mine extraction and your mine process. Okay, so just 3% is going to be the material that we're gonna be actually selling. All the other material is going to be with us, okay, as a tailings. So there are many conclusions that we can draw from these numbers, from these two numbers, okay? And we can use these two numbers in order to evaluate how good or bad our process is, okay? But let's come back to Paragominas, okay? And this is actually a real example, okay, people? And this picture is also from Paragominas. When they was designing the plant and they start to build the plant, they have this idea, okay, on how much is going to be the mass recovery, the mass yield. And in the end, okay, they end up the plant with something around 65% of mass recovery, 65. But they start to make some calculations after the plant ramp up. The ramp up is to put the plant to product, and that's going to take you something like 6 months in order to have everything stable in your processing plant. So they start to calculate and they came with this number, only 60%. So they had something like 5% of material missing. It should be recovering 65, but they were actually recovering 60%. Okay, so this number indicates what? Instead of having 35% of their material go into the tailings, they would actually having 40, but the plant was designed to have a recovery of a mass recovery of 70%. So take a look at this, okay? At the beginning, it should be only 30% of the material going to the tailing dams. Then in the end of the construction, they came with this number of 35, but actually they are delivering 40% to the tailing dams. So what's the problem with that? When I do a tailing dams, when I build up a tailing dams, I'm going to project this for 20 years. Yes, but one thing that you can directly draw from this figure is you're not going to be able to produce during 20 years because you're going to run out of space in your tailing dams before 20 years. Okay, before this. So another thing is, let's consider about money. Okay, let's consider about annual production. So this company is going to have an annual production of 7.5 million tons. Million, but if you take a look over here, it's another million tons over here. So it would be something like 7 billion tons. And let's consider that I'm going to be receiving something, oh, sorry, this is metric tons, okay? In this case, it's going to be 7.5 million tons, but million metric tons. So let's consider that I have a contract and I'm going to be able to sell my concentrate and I'm going to receive $36.59 per metric ton that I'm going to be delivering to my client. That would be something like 10% losses because, again, instead of having a recovery of 70%, I have a recovery only of 60%. And 10% of this is going to be $27.65 million per year. Okay, so $27 million out of my cash flow just because my mass recovery was reduced by 10%. Okay, and if you come with this to the stakeholders and try to justify to them why you lost $27 million, probably they're going to fire you because the scene is going to be something like this. You arrive, you present all the figures, they're going to come to you and said, okay, but how about the other $27 million that I was waiting to get? And you're going to tell them, oh, I just threw all of those in my tailing dams. Okay, so if you want to have those, just go to the tailing dams. They are right there waiting for you. They're not going to be pleased. Okay, they are not going to be pleased. And If you're not alone in this meeting, if you have people from the excavation and the hauling and the drilling and the blasting with you, they all are gonna point fingers on you and say, okay, but we deliver all the material. Okay, so you got the material and you're not doing your work properly. Okay, because that's all about reconciliation. They're gonna come to you and say, okay, we delivered there's 7 million tons to you, 7.5 million tons to you, and the grades was this grades because we made this estimation. We perform a lot of calculations, and we call this geostatistics. So we deliver the ore to you. If you don't, if you don't deliver this, if you're not able to produce this, that's all on you, and you'll be actually alone to stand your ground regarding mineral processing. Okay, so do these calculations as much as you can, perform all the chemicals assays that you were able to do it, because otherwise it's going to be your head in a spike in the end of the day. Okay, and definitely they're gonna come hard on you. Okay, so guys, another thing that we can also calculate or estimate is the ratio of concentration. Okay, so what is the ratio of concentration? We could imagine something like this: how much ore I have to feed my plant in order to produce 1 ton of concentrate. Okay, so that's quite good figure, because if you consider everything starts with the client. Okay, the client is always right and things like that. Yeah, I slightly disagree, but nevertheless, let's consider this. Okay, we have a contract, and this contract stands for a grade, definitely, and one mass. Okay, and probably a mass flow. So our client, he's going to buy only that. For example, he's going to buy 10 tons per hour of our material. So I have to deliver 10 tons per hour. If I produce more than 10 tons per hour, then I have to stock this material somewhere. Okay, I'm gonna have a concentrate silo or a concentrate stockpile. It doesn't matter, but I have to keep that with me. Okay, and we know that stock is money on the shelf. Okay, so I don't want to have stockpiles. I don't want to have an excess of production. I want to have a just-in-time production, and that's okay. That's a very good approach. I strongly agree and believe with you. But nevertheless, how much material then I have to extract from my mine, bring to the mineral processing plant, feed the mineral processing plant, work with that material in order to produce the exactly amount of material that I'm going to sell. Okay, so again, this is not a very difficult situation. Everybody can relate with that, but let's consider just like a bakery. Just for a second, let's consider a bakery. In the morning, the baker has to arrive to clean everything if there is some kind of dirty, and then he starts to prepare bread. If he prepare more bread than what he should be preparing, then he's going to lose money. Okay? If he prepare the same amount of money that he prepares every day, and in the end of the day, people arrive and there is no bread to sell, he's gonna lose money. Okay? Because he could be selling more bread than what he actually did. So he's gonna lose money. And the clients, they're not very satisfied if they arrive at your bakery and there is no bread. He's gonna come and said, oh, I'm never come back in here because I went there like 2 times and there was no bread, so I'm not coming back. Okay. And of course, we can make some slightly corrections during the day, try to make more bread or even to keep bread on the shelf. But nevertheless, the client can tell. Okay, the customers, they're going to be able to tell. Okay, that you're trying to sell old bread, that you're trying to make more bread and then you can't deliver. Okay, and the same goes to the mine. Okay, we can produce more than what we're going to sell, and we can produce less than what we should sell. Okay, because if they're not going to buy from us, they're going to buy from another company near us or from another company somewhere else in the world, but they're going to buy it. They can't stop their own production. Okay, and if you read anything about supply chains, they're going to always tell you have more than one supplier. Okay, so if this guy is buying from you, definitely he knows another supplier, and he can always go to the other supplier. Okay, so yeah, then again, if you want to design a mineral processing plant, the first thing to know is the market. Okay, the second thing to know is the market. Okay, so the first thing is how much mass the market can absorb, can actually buy it. And the second one is the grade. The third one is going to be also about the buyer. It's going to be about the particle size distribution. What is the particle size that my customer wants? And again, when I talk about this, let's go back to iron ore because it's one of the best examples. Okay, so the market is going to come for you, for example, and said, okay, I want to concentrate with 95% of hematite. Can you deliver? Yeah, of course. 95 of hematite coming out of the stock heap. You just go there and take as much as you want. Okay, and he comes to you and said, oh, I don't want as much as you have it on your stockpile. I just want like 1,000 tons per day. Okay, just go there and take 1,000 tons per day. And then the customer come back and said, I don't want that. I just want to return everything. And you're gonna ask him why? Because the material is too coarse. Okay, so you're selling me lump ore, and I need sinter feed because my production demands on sinter. Okay, and that's actually something real. You can sell iron ore in at least three ways. You can sell this as lump ore, you can sell this as sinter feed, is the material that's going to feed a sinter plant, and the sinter product you're going to deliver to the blast furnace. Okay, and then you're going to have pig iron coming out of the process. But the third thing that you can actually sell is pellet feed, and pellet feed is a very small particle size. Okay, it's very fine material, but on the other hand, you have a very good quality of the material in your hand, and this material is going to feed the pellets plant, and then you're going to feed your blast furnace or your directly reduction furnace with pellets. Okay, nevertheless, you need the material in the right particle size distribution. If you deliver in something different than that, your customer is going to return to you. Okay, definitely. So this is the three things that we can also think about the customers, and there is even more. Okay, there is a fourth thing. Okay, and that's about contaminants. And someone can tell, oh, but you just told me the grade. How do you should go back now to contaminants? There are four things now. Yeah, there are four things now, and the contaminants are paramount importance, because one thing is to come to me and say, okay, I want to concentrate with 95% hematite. Okay, and by hematite I mean the chemical composition similar to hematite. Of course, it could be part hematite, part goethite, but I want 95% coming straight from the X-ray fluorescence and standing iron oxide. Okay, Fe2O3. But if you deliver 5% phosphorus, okay, 5% phosphorus, they're going to return immediately this material to you, because no one can produce pig iron coming from hematite plus 5% phosphorus. It's going to ruin your steel. Okay, phosphorus and sulfur in the steel composition is going to fragilize the chemical structure and the chemical composition of the steel. The steel is going to break easily. It's going to be fragile steel. So they want phosphorus and sulfur something around 0 point something percent or a few ppms. So then again, you need to know this. You have to know this for sure. So that's why the fourth thing that we actually have to consider also regarding my customers is how much contaminants do you accept and what kind of elements do you consider a contaminant or not. I know that I have this target, 95% of iron oxide, but how about the other 5%? What can be with that material? Okay, and if you talk about iron ore, instantly they're going to think about silica. Okay, they're going to say something, oh, you have 95% iron ore, you have 5% silica, and that's not the case. Okay, that's not the case. You're not going to have only quartz and hematite. Okay, forget about that. You're going to have a lot of other stuff, and you need to quantify that stuff. Okay, so how about now our copper concentrate? It is possible to estimate the ratio of concentration. Of course, okay, we have everything in hands to do this. Okay, we still have the same feed, the same concentrate. I'm just going to divide one per the other and take a look at this. We're not going to calculate this as a percentage. Okay, that's going to be actually a real number, a decimal number. And in here we have something like 33. Our concentrate ratio of concentration would be 33. Okay, and then what kind of conclusions can I draw from this number? The first one is the maximum value that I can have for K, okay, would be how much? Would be infinite. Okay, if I have no concentrate, I have something divided by zero, I have infinite. So K could be as big as you like. Okay, that's not a limitation. But the smallest amount of K is going to be 1. Okay, so again, if you don't have tailings, you have everything that you put in your flotation, you take out of your flotation. That's perfect because your K is going to be 1. Okay, and if you consider the mass recovery or the mass yield is going to be 100%. Every single material that I fed to my equipment, I took it back. So that's going to be great. But then again, you have no concentration. If I calculate the recovery, I'm going to see that I have no concentration. Okay, and I need concentration. I need to increase what? I need to increase the grade of my elements, my desired elements. So I need to have concentration. And that's why if I have high concentration, probably I'm going to have what? A high, no, I'm going to have a low mass yield. Okay, so high recovery, low mass yield or mass recovery. Okay, and the same goes to the K. And K is important for us when we talk about gold. Okay, so consider this: in a good scenario, your gold mass recovery, mass yield is going to be something like 5% up 10%. So when I estimate this, I have 15,000 metric tons divided by only 150 metric tons. And then my K is going to be good numbers, high numbers. Okay, so if you consider iron ore, K is going to be small. Gold ore, K is going to be great, big. It's going to be great, big. And just have this in mind. Okay, you just can't compare Ks. You can compare definitely recover. You can compare mass yield, but you can't compare directly Ks. So what you're going to do with key is you can compare if you're working with the same ore. Then definitely you can have this discussion. So a high key is good for business. Definitely is good for business if you're in the business when you have low grade feed. Okay, so if you have low grade feed, it's good for business. Okay, but if you had high grade feed, we're talking now about iron ore, manganese, and things like that. A high K is not going to be something good. You're going to focus on low K. Okay, but again, another thing that we can also start to think about this is how about my mineral processing plant? Because I can have the recoveries calculated for one flotation cell. But as I mentioned to you last lecture, I can have many flotation cells in my process. So maybe the key is going to be different from one cell to the another. And that's the thing that I be looking for. Okay, so in part of my process, I want a big key. In another part of the process, I want a small key, and so on. Okay, we're gonna take care of this in the future. Guys, another thing that we can also estimate, and this is not standard. Okay, so if you go to some books, probably they're not even going to mention this to you, but other books you can see this. And when we talk about also industrial operations, some companies they evaluate this, others they just don't care. It's about solid split. Okay, what is solid split? Is the inverse of concentrate ratio. Okay, so it's the opposite of the concentrate ratio, and now in percentage. Okay, so instead of dividing the feed for the concentrate, now I have concentrate under the feed. Okay, and then I'm going to multiply by 100%, and then I know for sure how is the split that I have between my solids, which means how much material I'm sending to the concentrate and how much material in percentage I'm sending to the tailings. Okay, so a mass split of 50% is going to give me what kind of idea? The material is going to be 50-50, 50 for the concentrate, 50 for the tailings. Okay, so if I have something like 70%, so that's quite good. 70% of my material is going to the concentrate, and I'm producing only 30% as tailings. Okay, so this actually is something that we can evaluate. Okay, it's not standard, but we can. And another also number that we can evaluate, again, not very used or widely used, but it's possible that you can find this in some books, is the enrichment ratio. Okay, and the enrichment ratio is going to be almost the same things that I mentioned for you before, but now focusing on grade. Okay, so if I divide the concentrate grade by the feed grade, I can calculate the range enrichment ratio. Okay, and again, if you talk about gold, they always look for a high enrichment ratio. Why? Because they feed the plant with 1 ppm, okay, and they want to have something come out of that. When we talk about gold, normally we talk about gram per ton, okay, so GPT, gram per tons, or ppm is going to be the same, but people prefer to say GPT, okay, gram per ton. And how about our first example again? Could we calculate the ratio of enrichment, the RE? Definitely, okay. And I just have to divide the concentrate grade by the feed grade, and I'm gonna have something like 28, okay, 28 times richer. So that's the figure that I have to keep in mind, okay. So my material is going to feed my plant, and I'm going to take out of that as concentrate a material 28 times richer than what I actually feed my processing plant. Okay, that's a very good number. Okay, that's a very good number. So a high RE is good for business. Normally, it is good for business. Okay, because if you have a small RE, what I can draw from that is my mineral processing plant is not doing much. Okay, so I fed my material and I reclaim the material is almost the same grade. So I'm not doing actually much with that. So I need a high RE. So to summarize, that's the variables that I present to you so far. Okay, so I have for the feed capital and lower cases, for feed, concentrate, and tailings, and also I can calculate ratio of concentration, recovery, mass recovery or mass yield, ratio of enrichment, and so on. So now we have 6 variables, okay, so 6 inputs, and I have 4 outputs from my mineral processing plant as a mass balancing, okay? But normally that's not what's gonna happen, okay? So many times what I'm gonna have is a byproduct, and I'm gonna sell this, so it's going to be like a co-product. So what I'm gonna actually have is a bimetallic company, okay? And that's pretty standard when you talk about copper. You're always gonna produce copper and something else, lead and something else, zinc and something else, molybdenum and something else, and so on, okay? And eventually this something else could be silver, could be gold, okay? And yes, you have to keep in mind that this something else could be something that is going to make your stakeholders quite happy, okay? So that's why you have to produce those. So let's take a look at this. We have one feed and one tailings, okay? Just one. But I have 2 products, and that's why my tailings is also addressed as product 3, okay? We could make this analogy, okay, having 3 products. Product 1 is going to be market, product 2 the same, and product 3 tailings, okay? How about this? It's going to be the same equations? No, the equation is going to change. Why? Because now I have copper. Let's take a breath and understand this. I have copper in my feed, okay? I know this. I'm feeding my plant, so there is copper in my feed. I have copper in my concentrate. Definitely, I'm gonna market to this. So I have copper in my concentrate. Makes a lot of sense. But I told you before that I'm going to always lose some of my element, my intercept element in our tailings. So yes, I have copper in my tailings. But then again, I have another product now. I have a zinc concentrate. So if I have a zinc concentrate, I have copper in my zinc concentrate. I'm always going to have copper in all the flows that you can imagine. So I have now another grade for copper, and that's going to be in the zinc concentrate. So I have now 4 grades for copper. If I take a look at the zinc, it's going to be the same, okay? I'm going to be zinc in the feed, in the tailings, in the zinc concentrate, but also in the copper concentrate. It's going to be quite hard for me to produce a copper concentrate without any zinc, okay? I'm gonna always produce copper with a little bit of zinc, okay? And that's something that we can also have in mind, Okay, so if your geology, if your local geology, it's about copper associated with zinc, you're always going to produce copper plus zinc. Okay, even if you don't like it, if you don't want it, your copper is going to have traces of zinc. Okay, and if your customer don't allow zinc in their product, they're not going to be your customer. They're going to be copper from somewhere else, from some other mine that doesn't have zinc in their composition. And trust me, it's going to be really expensive in trying to remove the zinc from your concentrate. Sometimes it just doesn't pay out. Okay, so people from the metallurgy, they can do this easily. So you can actually buy this copper plus zinc, and during your metallurgical process, you get rid of the zinc. Okay, and that's something that you can and should be doing. Okay, so take a look at this on a different approach, on a different point of view. But how about if I have not just two, but if I have copper, zinc, molybdenum, I don't know, silver, and gold? Then I'm gonna increase my table, and I'm gonna have the copper assays for all the flows, the zinc assay for all the flows, and the other elements for all flows. Okay, so here in Catalão, as I mentioned and showed to you before, when we talk about niobium plant, we have carbonate flotation. Okay, and when I perform this carbonate flotation, I lose niobium. Then I have silica flotation or silicates flotation, and I lose niobium too. Then I have the niobium flotation, and I have another tailings come out of this flotation plant, and then I lose niobium again. And in the end, I have the niobium concentrate. So if I'm going to make the correct estimations about the recoveries, then I have to trace all of the niobium losses and all of the niobium grades in my process, input in this table, and perform all the calculations. So yes, it's going to give me a lot of work, but then again, I can do it. Okay, so those are the two equations that I can actually use in order to calculate the copper concentrate, and the copper concentrate in here is just C, okay, and the zinc concentration that I'm representing as Z. Okay, so just take a look at this. If you have the feed and the grades, you just need to multiply and make some subtractions, and you're good to go. Okay, so that actually give you a lot of work, and I'm gonna let you guys do this work in a few seconds. Okay, but then again, it's easy to do this. You just have to make the subtractions, multiplications, like 4 multiplications and 1 division, and then you're good to go. Okay, so let's consider this now. Okay, how about try to make things simple? Would be possible, or is it possible to simplify those equations? It is. Okay, I can do something like this. I can add an additional product. Okay, I can imagine something like a copper tail, and the copper tail would be the zinc feed. Okay, so I call this CT, copper tail. Okay, and if I consider this, I can try to figure it out, this copper tail, as another flow. And that's why you have 4 figures at the beginning, and now I have a 50 one. I have a 50 assay, chemical assay, and it's going to be the copper tailings. Okay, and again, if the copper tailings is exactly the zinc feed. So before I move forward, let's take a step back, okay, and let's take a look at this again. So this is exactly what I'm describing to you. So take a look at this. There is no tailings, there is no copper tailings if copper is the first product over here, because I take all of the copper tailings, and it's going to be represented by this red dot over here. Okay, so I took all of the copper tailings and deliver to the zinc mineral processing plant, or the zinc flotation plant. Okay, and then after I have the zinc with me, then I have the tailings. So now I can do what? I'm able to input this, and I can do something like this. I can do the mass balance of all of this, and then I can do another mass balance of this. Okay, so I can split down my mass balance into 2. Okay, and then I can evaluate correctly the figures that I want to do. Okay, so by doing this, our equations can be simplified something like this. Okay, so copper plus copper tailings is just like 1, because I'm considering now, just for this example, that my feed is 1. Okay, so let's input the grades, and the grades for the copper feed is C2, and the grade for the copper tailings is going to be C5, okay? And the feed is C1, so C1 plus 1, C1, okay? And if I now consider this, but taking into consideration what? That situation that I mentioned to you, that the copper tailings is the zinc feed, okay? So this equation in here, it comes only about copper. And this equation over here, that's the zinc feed, okay? And they're the same. So if I subtract these two equations, let's call this equation A out of equation B, what I'm gonna have is this one, okay? I'm just perform the calculation over here. As you can see, the CT I'm going to remove, and this I just put in evidence C over here, okay? So coming back for the feed as F, okay? So I'm going to abort that F being just a unit 1, okay? I don't want to work with that. I can bring back the F, okay? What I'm have is the copper concentrate is going to be estimated like this, okay? What I need is the feed grade, and the copper tailings grade, okay? And this is the copper concentrate grade, okay? And if I go to zinc, it's going to be the same, but talking only about zinc grades. So it's easier, and it's possible, it's doable. You can do this, you definitely can do this. You just isolate the copper tailings as a new product now, or a new byproduct, and the copper tailings is going to be exactly the zinc feed, okay? And by doing this, I can evaluate. So guys, now I have an example for you, and I want you to pause this video after we talk about the variables over here, and you try to calculate everything in here. So I'm gonna do the same with my students. Today I have 5 students with me here, and I thank you guys for that. But I want you guys to try to evaluate this, and then I come back with the results. So now we have a copper zinc plant, okay? And I want to evaluate now what? I have say the copper tailings, and the copper tailings is going to be 0.55% of copper, and I have a zinc concentrate with 20.9%, it's Z5, okay, respectively. And consider the the 20.9 is the zinc feed, okay? So this two over here, so this one and this one, this is the CT, okay? So this is CT regarding copper and the CT regarding zinc. So this in here is the zinc feed, okay? So consider that now we're producing a zinc concentrate with 54.87%, okay? And the zinc tailings with 9.85%. Use the same figures for copper that we were using before, and let's try to calculate now how it's the amount of copper that we're producing as a concentrate, tailings, and also for the zinc, okay? So again, pause the video now and come back in a few minutes after you have this result. So let's take a look at the results, okay? So as you can see, we can estimate C and Z in the directly process. We just need to input this information in the equations, and then we can calculate also the recoveries, the copper recovery and the zinc recovery. Okay, so as soon as you got C and Z and you have F, okay, you have everything that you need to calculate everything. So one thing that I want to call your attention on it is, if you try to calculate only the copper recovery without considering the losses on the zinc, you're not going to be able to reach the same number, okay? So you have to take into consideration that copper in, copper out, okay? And copper in for me is the feed. Copper out is not only copper concentrate, it's copper concentrate plus copper tailings, okay? And copper tailings is going to be what? The zinc feed. Then I have the same procedure with zinc, okay? If you want, you can also map copper in all the flows, okay? And that would be the copper concentrate, the zinc concentrate, and the tailings. Okay? In the end, it's going to be the same. So if you apply the first set of equations or the second set of equations, the result should be the same, okay? And I hope the result is the same. Go ahead, Ramon. Please feel free.
Okay. I don't know if I missed something, but the feed. Did you give the feed the mass of the feed?
Is the same feed that we used before, 15,000.
Or 50,000?
Yes, tons per month, tons per day.
Okay.
Okay, so just input the 15,000 and you can reach those numbers. Okay,
Okay.
so let's move forward a little bit. So this is the case. Okay, so if you consider, you can also calculate or estimate the key for copper and the key for zinc, and those results you can see they are quite different. Okay, and why they are so different? Because I'm considering the input of zinc as 20.9% would be the feed of the zinc coming from the tailings of the copper, and that's why you're gonna end up having this number so low. And the K for the copper, since the copper is only 0.555%, okay, you're gonna end up having the key so big like this. And you can also calculate the mass recovery and so on. Okay, so that was the second example, and then we have a third example. Okay, so this one is slightly different from the previous one. Why? Because I want to estimate pretty much everything: the solid split, the ratio of concentrate, the ratio of enrichment, and also the zinc recovery. Okay, and in this case, as you can see, we have a feed of zinc flotation, and we have the grade of zinc over here, the assay, and we have also over here the zinc grade on the concentrate and the zinc grade on the tailings. Just take a look that we don't have any flows. Okay, so this is also a standard situation for mineral processing plants, because sometimes it's quite difficult to correctly measure the flows. So we don't make all the calculations without any flows. Okay, and how can we do this? We can go straight for the solid split. Okay, because we have again all the grades, and we have this solid split as 6.67%. With this, we can also estimate what the one under this number, which will be the enrichment ratio, which is the inverse of the solid split. So I just have to invert this, of course, without considering the percentage over here, and we have 13.25. So as you can see, one thing fits into the other, and that's why we can solve this. The same goes for K. We can evaluate K without any kind of flows. I just need grades. So let's do this, and we end up having the number of almost 15 for K. And last not least, we can just input all the grades into the recovery, and we got 88.36% of recovery. Just take a look at this and imagine the same scenario. We can't talk about mass yield, okay, because we don't know about mass. But one thing that we can also do is consider the feed as just one, okay? So we take one unit as being the feed, and then we can evaluate all the rest. Okay? That's possible. Okay, and then you can come with the calculations like this. For every ton that I feed my plant, how many kilograms I'm going to produce as zinc concentrate. Okay, so this is also works and helps a lot when you don't have the correct amounts of the flows. Okay, so just another regular example. But guys, the real life, Ramon, do you want to ask something? Okay, go ahead.
Yes. In this case, can we consider the SS like mass recovery?
No, you can consider SS as mass split. Okay, what will be then the mass split? So let's consider this black box over here. So I have the feed goes in, and I had the concentrate out, and I have the tailings out. What can I consider? Oh, sorry, let me use capital T over here. Okay, capital. What can I consider as the solid split is how much material I'm sending to the concentrate in relation to the tailings. So again, if I have something like 50%, I know that the split is 1-to-1. Okay, so 50% to the concentrate, 50% to the tailings. If I have something like 70%, I know that I have 70%, 70% on the concentrate and just 30% on the tailings. So the SS is not the mass yield, but it's not even related with the mass yield, because mass yield is going to be directly concentrate and feed. Okay, so I'm going to take a look at these two, and the equation is concentrate under the feed multiplied by 100%. Okay, and when we talk about mass split, I just want to know the split of the mass between concentrate and tailings. Okay, in the end is also about masses. Okay, but when we talk about mass yields, I'm not talking about the tailings. I'm just talking about concentrate and feed. And when I talk about solid split, I'm talking about concentrate and tailings. Okay?
Okay.
That's great. So let's move forward. Guys, in the real world, what we have is something like this, okay? And this example, it's quite simple example, okay? I'm gonna let you evaluate this, but let's take a look at this again, copper concentration plant, okay? We have a breakage, and then we have our feed over here. We have 100 tons per hour, okay? And this in situ rock breakage, what you can imagine about this, we're talking about blasting, okay? So for example, we're performing a blasting, and then it's going to produce 100 tons per hour, and I'm going to feed this in the primary crusher, secondary crusher. Then I have classification, and as you can see over here, we have a closed circuit on this secondary crushing, and we're going to get to the closed circuit in the future. Then we have grinding, and also we have in here another closed circuit for grinding. And then we have solid liquid separation. It's quite strange to have the solid liquid separation over here because we didn't have any flotation yet or anything like that. But nevertheless, let's consider that somewhere around here we had a flotation, okay? And then we have another solid liquid separation over here and here. So the problem is right here. This should be right in flotation over here. But since I took this example from this website, I just kept everything as the same, okay? But it should be written in this box, flotation. Then we have solid liquid separation for the concentrate and solid liquid separation for the tailings. Now makes sense. Okay, now the flow sheet makes sense. So what do we know for sure? That we have a feed grade, a cutoff grade of 0.5% copper, okay? And we produce a tailings with 0.14% copper, and we are able to produce a copper concentrate of 24.5%, okay? And regarding the flows, we know that we feed our mineral processing plant with 100 tons per hour, and we can produce only 1.5 tons per hour of copper concentrate. All the rest is going to be tailings, and using the first equation, 98.5%. So what you want to do now is calculate the mass yield and the recovery for this flow sheet presented over here. So it's simple to do this, but just to make sure that you guys can also do this, I'm gonna allow you like 5 minutes, just perform these two calculations, and we come back. And so for you who is watching us on the YouTube, just pause the video, and then we come back with the results. Okay? Thank you. And we're back, and let's see our results, and I hope that you could actually get this right, okay? So in here, we can go straight for the mass recovery because we have all the grades, but if you want to start with also recover, that's not a problem at all. We can solve both because we don't need to finish one in order to go to the next one. And the mass recovery, or the mass yield, is going to be 1.5%, okay? So one thing that you have to be careful is always try to do these calculations using all the data that you have, okay? So in this case, the results are going to be the same, but if you're going to do this in your mineral processing plant, maybe that's not going to be the case, okay? So just try it. If you have all the flows and you have all the assays, just go and try to calculate all the recoveries using both methods, okay? So the first one, 1.5%. And if I go to the second one, to the recovery, we're gonna see that we have 73.5%. So that's going to be standard, okay? It's expected for us to have a high metallurgical or recovery and a low mass recovery, especially when we talk about materials like ores, if I have small or low grade concentration, okay, low grade feed, sorry, and I want to have a high grade concentrate. Okay, and that's going to be standard. The recoveries have to be high and the mass yield is going to be low, unfortunately, okay? So in here we have another example, and it's again a big one, okay? So if you want, just pause the video, go to that equations that I showed to you before, and then come back. I'm not gonna allow the guys time to solve this one they're going to solve later. But in here I prepare for you an example regarding lead and zinc. And again, it's a real example. It has some fundamentals, okay? And then we have a feed of 600 tons per hour, and we have all the assays. So different from the first one, now we have all the assays. So if you don't want, you don't need to have that kind of copper tailings being the zinc feed. You can go straight to the equations and just replace the numbers and evaluate the ratios, and also the flows. Okay, so suit yourself. You can choose one on the or the other, but that's the results that you're gonna get. Okay, as you can see over here, we have 600 tons per hour feeding our mineral processing plant. We have just 48 tons of PB concentrate, and we have 73 tons of ZN zinc concentrate. Okay, and the tailings we have something around 408 tons. And it is a lot, but I think with this you can better understand why we have so many tails. Okay, so many tailings, because it's virtually impossible to recover more material than what we're already doing. And even if I recovered 100% of all lead and all zinc, I still have a lot of other components different than zinc and lead. What we can try to do is produce other things out of that ore, just like other byproducts, other concentrates. Okay, so I brought some examples for you for us to finish this part of the chapter about the real world. Okay, how it's going to be the real world. So instead of just producing lead and zinc, I'm going to also have some copper, some silver. Okay, and as you can see over here, the silver is quite good, 2% of silver. Okay, it's nothing low, and copper just 0.33%. Okay, so this is a very low grade of copper. And why should I keep trying to take a look at this copper? Because if I look only at the copper, probably the math is not going to close and the economics is going to be terrible. I'm not going to be feasible to produce this copper. But if I try to produce copper plus silver, zinc, and lead, then I can profit from that. Okay, and that's exactly what I'm going to do. And as you can see over here, we're going to produce a copper concentrate with 22%. I'm just going to round this 22%. Okay, and I'm going to end up having something like 50% of silver on this copper concentrate. And I know it's a lot, and I'm going to remove this later on the hydrometallurgy or pyrometallurgy, depends on your route. And on the lead concentrate, we're going to have something like 42%, 10% zinc, and 15% of silver. And we're going to have to take care of this. And we're going to have to take care of this, and we will. And for the zinc concentrate, that's very good concentrate, 57%. Okay, and the other elements quite low. And last not least, if you take a look at the tailings, they are small values, okay, compared with the feed. But just take a look at this. My cutoff grade for copper was 33, 0.33. And I'm dumping on my tailing dams 0.15, almost half, okay? And silver, the same, half. Lead, the same, almost half, okay? So what I really recovered was zinc, okay? And when I take a look at this, it's quite strange because I have something like half of the grades of my mine on my tailing dams. But imagine this, in the future, I'm gonna run out of a mine, or the grades on the mine are going to reduce, and then I can go back to my tailing dams and try to recover even more of those elements from my tailing dams. And that's what we're doing nowadays in many places around the world. Okay, so Europe is doing this, Brazil, we're reclaiming a lot of tailing dams, especially after the accidents that we had over the past few years. Okay, so now we're trying to reclaim our tailing dams, recover some valuable out of our tailing dams, and then stockpile dry tailings. Okay, it's safer, it's more expensive, of course, but it's safer than the tailing dams. So that's something that we're doing right now. Another example from the real world would be something like this. So we have the mill, we have a Hofer flotation stage, and then we have a scavenger, a cleaner, recleaner, and a final cleaner. And then we have tailings and concentrate. And I put in here all the figures that you need to perform all of your calculations. So I strongly advise you to take these numbers and try to calculate all the recoveries, all the flows, and you're going to see that it's possible. Okay, and as soon as you get the random of it, you can also calculate something that is not written but showing here, which is the circulating load. Okay, so every time that we have this arrow coming back to a stage previous than the first one, then the actual one, then we have this circulating load. Okay, in this case, we can see one. If you take a look at the rougher flotation cell, okay, we take the rougher concentrate and send it to the cleaner. But the cleaner tailings still have some values on it. And so I take back this cleaner tailings and I'm going to feed my rougher flotation also with the cleaner tailings. And that goes for also for the recleaner. I'm going to take the cleaner concentrate and I'm going to feed the recleaner. And the recleaner tailings become also the feed of the cleaner station. And that's go on until the final cleaner, and then we have the final concentrate. So as you can see over here, our copper assay is only 0.53%, okay? But if you take a look at the mill, every copper that goes in goes out of the mill. So the copper recovery in the mill is of course 100%, okay? And if you take a look at the mass in the mill, again, if we put mass in, mass out. So we have a mass flow of 709 tons per hour, and that's going to be the feed and the product of the mill, okay? If we added the particle size distribution, then we had another chapter just to take a look at it, because mass goes into the mill, but in one specific particle size distribution, and mass go out of the mill in another particle size distribution, and I have to take this into consideration. And again, energy goes in, water goes in, and I know that energy goes out and water also goes out. In this chapter, I only mention ore, okay? But you can do everything that I did for ore for water too, okay? And it's quite important for us. So let's move ahead. We have the scavenger, we have the cleaner, and we have also the recleaner and the final cleaner. So our final concentrate in the end of the day is gonna be what? 33% of copper, but just 10 tons per hour. So we move from 709 tons per hour to only 10 tons per hour. But what we want to sell is just this, 10 tons per hour. But again, that's what makes us be here. It's not easy. Okay, it's a very complex process, and yes, we have to reduce everything. So I'm going to show you just a few more slides about circulating load and how I'd like to do this. Okay, so normally when we have situations like this, I have a flotation cell over here, and on the top in the Spanish, you can see our exercise. So I have the material feeding the flotation cell. I know the solids percentage, and I know also the lead assay, and I know what is coming out of the flotation, but I know only the lead assay on the concentrate, and I know the lead assay on the tailings. And one other data that I have is the solid percentage. So if you take a look over here, I'm missing 3 values, okay, out of this. And if I try to answer this, I'm gonna see that I can't couple the equations because I have more variables than I have equations. So how can I do this? How can I actually solve this? I can use exactly this. I can use Excel solver, okay? So the solver on Excel is an interactive way to solve problems. What I mean by this is Excel is going to take one value and it can evaluate the error. So if the error is not okay, you can change this value, okay? You do this automatically and you evaluate again your error. And then you just take a look if you have a convergency of this error into the number that you're going to estimate. For example, 0. In this case, I'm going to show you guys how to prepare Excel and how to do this in order to reach an error that tends to 0. Of course, it's not going to be 0. In this case, I could reach an error of 0, but it's going to tend into 0. And that's going to be good enough, okay? So what I have to do is I go to Excel, I prepare my table, and I'm going to put the same values that I have, okay? I'm going to pass on to Excel as much information as I can. So as you can see over here, I just translate this box from here into this box in here. So the mass flow is over here, the solid percentage is over here, and the lead assay is right here. And over here I have what? I have the lead assay, and I didn't have this number. It should be written like this. So I have in here also the lead grade. And in here, as you can see, different from here, instead of having just one variable, I have two. Why? Because I just changed this solid percentage for this. Okay, so it's a slightly different example, but in the end, it's going to be the same. So I have to input on Excel as much equations as I can. Okay, so the first equation that I can actually input in Excel is what? It's our mass balancing. Okay, so feed would be equal what? Concentrate plus tailings. Okay, so let's do this. So I came here and just wrote this: A equal B plus C. Okay, why I changed the name, the numbers, just to match the Excel columns. Okay, so I have my feed on column A, my concentrate on column B, and my tailings on column C. Okay, just to make things a little bit simpler for me. And if I put also numbers, I'm gonna have something like this: 352 equals P plus C. Okay, but how can I roll this on Excel? Okay, I can't just type this on Excel. So on Excel, I'm gonna do something like this: equal, and then Excel recognize that it's coming an equation, okay? And it has to evaluate this equation. So I'm gonna use this cell. So instead of putting the cell reference, I'm just gonna put the number in here, okay? 352 minus what? C minus T. I don't know C and T, so that's I'm going to put these variables. And then the other equation that I have is this one. And this equation gives me what? The amount of material that I want to work with. Okay, so the useful material. Okay, so I'm going to multiply the assay plus the tonnage or the tonnage flow. And then I have this mass split. And then I have a second equation. And as you can see over here, I have on this second equation three variables. Okay, I don't know B, I don't know small k, lowercase c, and I don't know uppercase c. So I have B, C, and C. So now I have two equations and three variables. Okay, so I go to the another one. Okay, and this equation over here gives me what? Water. Okay, so I'm inputting right now the water split. So this line that I'm put on the variable, it's correlating directly with the water flow. So by multiplying that all, I have what? Water split. Okay, so going to Excel, the first thing that I have to do is enable the solver parameter. So you go to File, Options, and turn on solver. Okay, it's on the supplementary. Oh, sorry, my dog is running wild. It's the supplementary tab. Okay, and unfortunately in here my Excel is all in Portuguese, so you're gonna see Excel in Portuguese and I can't translate that, so I'm sorry about that. But as soon as you enable solver and go to data solver, you're gonna have this screen for you. It's going just to pop up for you this solver parameters. Okay, and it's quite easy to work with that. So the first thing that you have to do is to define the solver parameter, and has to be just one single cell on Excel, and that's your objective function. Okay, so in my case, I want my objective function being what? Being 0. Okay, because I'm going to put for Excel that I want to have my mass balance error being 0. Okay, so I went there and just click and point to the Excel cell that I want to have my objective function. Okay, because I previously typed in the objective function on that cell. Okay, another thing that I have to do is enter restrictions. Okay, so what kind of restrictions I have to give to Excel? For example, no flows should be 0. That's one thing that is quite feasible. Okay, another thing is no flows should be without water. It's impossible to have a flotation and one of the flows came back completely dry. So I can also put these restrictions. And restrictions in Excel, in this case, is going to be what? The cell and what kind of restriction I want to apply to it. So the cell could be greater than one value, smaller than other value, and so on. Okay. Last not least, I have to tell Excel what kind of cells it can commute values. It can change values. So coming back to this figure over here, and let me just clean this screen. So those cells that are represented in pink or reddish, Okay, those are the cells that I allowed Excel to swap values, to change values. So the solver method is going to be what? To take care of the cells in order to meet the restrictions and also the objective functions. So Excel is going to start to change values. And it's going to change this and doing this process until it reaches the objective function that I defined to it. And it's going to do this always in order to minimize or maximize your objective function. Okay, so it depends on what you input on Excel, you're gonna come from that, you're gonna get from that. Okay, so in this case, I'm just going to add restrictions, and for example, I'm just gonna put restrictions as 0. Okay, because I want to have the errors being 0. So as you can see over here, my objective function, I want it to have 0 as value. Why? Because my objective function would be this one. Okay, feed equals concentrate plus tailings. So this is going to be 352 minus C minus T, and I want this to become 0. Okay, I don't want any error. And I add also this other parameters being as error. Okay, I just have to click in solve, okay, or solve, and then Excel is going to do all the tricks. Okay, and it's going to come back for me, hopefully, with a box like this. Okay, this box means that Excel could find one solution for my problem. Okay, so if I click on OK, it's going to close this and going to show me back on that my spreadsheet from the beginning, and on that spreadsheet I'm going to be able to see the values that Excel found to me. Okay, one thing that has to be also said about this is Excel is going to take the first values that you add to the cells that you want it to change. So it's quite confusing, I know, but consider this. Excel needs a seed in order to start the calculations. So if you go to that cell and keep it completely clean, Excel is going to assume that the value is 0. Okay, but on the other hand, if you went to the cell and put, oh, I think the cell should be from 0 up to 152. Okay, so let's take a number better. 42. Okay, 42 is a number with a lot of meanings. Okay, I'm gonna type that 42, and then Excel is going to start its numeric method on 42. Okay, and maybe we can end up having 2 different possible answers for the same problem. That can happen. Okay, so why I'm telling you this? Because sometimes we have just one maximum point or minimum point in that interval of values. Okay, from 0 to 100. But then if I go out of 0 to 100, then I can have more maximums and minimum points. Okay, but my grade, I say, let's just go from 0 to 100. So it's okay, I'm safe from 0 to 100. But then again, maybe my equation ranging from 0 to 100 has more than one minimum point. Okay, and in this case, it's quite helpful that we understand how Excel deals with the seeds, and then we can understand why it's giving me one result, and if I change the seed, I'm going to get a different result. Okay, so for more complex systems, you can end up having more than one answer, and this answer is going to actually satisfy, if not all, but part of your restrictions. That's why you have to be extra careful. Okay, but it works. And another thing that you can do, another restriction sets that you can also type in the Excel is this one. So in this one, I did things like this. I set Excel that one flow cannot be higher than 352. Okay, this is impossible, because if my mass goes in is 352, all the masses coming out has to be smaller than or equal to 352. Okay, another thing that I mentioned to Excel is all the flows have to be greater than 0. So I don't want the Excel give me the result something like this. Oh, if you put 352 tons per hour in your flotation cell, you're gonna end up having 352 tons per hour of concentrate. Okay, I don't want this. I want the Excel to take into consideration that part of this material has to go to the tailings. It's obliged to do this. Okay, so it's compulsory. And if you want, you can add up more restrictions to your system if that's the case. And it can actually help Excel to be more assertive. Okay, so if you put a lot of restrictions, you're not going to commit any errors, I hope, but in the end, you can actually end up having a result that's going to fit you better. Okay, so in the end, you can also have something like this. Okay, so this is a slightly more complicated example. Okay, and I make sure to bring this to you. I like this example a lot because it's for grinding, okay, especially for milling. It's a closed circuit for a ball mill, okay. And when you talk about ball mill, you always think that that's quite simple. It's quite simple. Mass in, mass out. Sure, mass in, mass out. But when you have a circulating load, and that's what the cyclone is giving to me, then I have two masses in. And if I have water, then I have three masses in, okay? But then again, after taking back my material from my mill, I have to dilute my feed, okay? I have to dilute my pool because normally I'm gonna put something like 95% of solids into the mill, okay? It's too much solid. Then I add water, okay? And that's what I'm doing on stage 2. I'm adding water. So this water is just to reduce the solid percentage up to 70%. 70%, my mill can work with that, okay? It's okay. But after taking this material after the mill, and it's going to be something like 70% also, I have to reduce the solid percentage, for example, to 50%. And how can I do this? Adding more water, okay? So now the system became a little bit more complex because I have more variables. And I can write down all of those equations. Okay? And that's quite good if you can actually look to one of the feeds and start to think, what kind of equation can I write down? And as you can see over here, it's just for the first equation. Okay, just mass in, mass out, or water content multiplied by the mass in order to allow me to calculate the mass split and the water split in the pulp. Okay, and Excel can do this for me easily. And in this case, as you can see over here, I ask Excel to calculate how much water I have to add, okay? And this water over here has 0% solids, okay? But I can change that. And this other water over here, I also Excel to calculate the dilution water for me in both stages. And in here, I was a little bit more bolder. I took this and asked Excel to consider 1% solid on this other water because I'm recirculating water on a mineral processing plant, so it makes a lot of sense having some solids on this water. And I ask Excel also to make this balance over here, over here, over here, here, and finally here. So what I gave to Excel, I gave to Excel one mass, okay? Only the new feed of my ball mill, okay? And then I gave it some water partitions, okay? Just a few. And Excel can do all the rest. And it works very nicely, okay? So in the end, you can put all your mineral processing on an Excel sheet, and you can just hit a button if you want, and Excel perform all the calculations. Okay, so we have a lecture here in our university. I normally teach this lecture, and in the end of the lecture, what you have to do and deliver to me, your final product is an Excel sheet with every single unit from a mineral processing plant on it, and Excel do all the mass and water balance on it, okay, and estimate all of the key parameters like recoveries, enrichment, and so on. Okay, so it's quite nice and it's quite good if you can actually do it by yourself. Okay, I promise that I'm going to try to translate everything into English. Okay, I just didn't have time enough to do this, but I can translate the Excel part, but you can figure it out in English. Just open Excel and you're going to see exactly what I showed you in here. So I don't think you're going to have any trouble or any problems just running Solver on Excel. Okay, worst case scenario, just browse online. There are plenty of how-tos explain to you how to use Excel Solver, and it's a very powerful tool. Okay, you can even choose how you want Excel to perform this calculation, but again, it's a very, very powerful tool. So guys, I hope that you liked today's lecture. I thank you so much for being here, okay, and I appreciate very much if you can follow us on YouTube and also click and comment on this video. Okay, so next lecture we're going to talk, our last lecture, we're going to talk about water, and we're going to talk about remove water from our pulp. So the lecture is going to be dewatering. Okay, and then with that we finish our initiative and ifs, and we finish this course. Okay, so thank you very much and have a nice weekend. Bye bye.